Welcome to the third lesson. Now in this lesson we have two topics that we're going to be covering. The first is going to be transformations with nonlinear functions, and then we're going to look at some applications of functions, and in particular variation, where variation is a type of proportionality. So let's start off with the whole graphing business. So we're going to do a quick little review of some nonlinear functions that we graphed in the last lesson. There was 3 examples that we did of nonlinear functions from the last lesson that I want to redo. And the reason I want to redo them and just go over them is because these are functions I expect you to be able to graph without point plotting, just to know and to basically memorize what these graphs look like. So if we were to transform them, and by transform I mean to shift them up, down, left, or right, or to flip them, then you can just say, all right, well, if I shift this, I already know how to graph it once it's shifted. And that's kind of the main idea of this particular lesson. So a refresher for y equals x squared. Let me go ahead and graph it first and then remind you of some of the ordered pairs. So remember that this is the one that looks like a parabola. And so y equals x squared looks like a parabola. Again, we don't want to do point plotting on this, but the points that you did find in the last lesson consisted of -3, -2, -1, 0, 1, 2, and 3. And you squared each of those values. The y values that came out were 0, 1, 4, and 9. So if we look at those values there, those are your perfect squares. We're going to have what we call a 149 rule that we're going to look at for graphing these parabolas, which basically means if you start at the vertex is kind of the bottom point. If you start there, if you take a step in either direction, left or right, your next step is to go up by 1. If you take 2 steps over, then your next thing is go up by 4. And that's really what's going on then. 3 steps over, you're going to go up by 9. So each time you take a step over, you go up by 1, then 4, then 9. And these counts that we do are from the vertex. So it's not like with our straight lines, with our linear equations, when we counted from the previous point. It's always from where the vertex was that we count up by 1. From the vertex, we count up by 4. From the vertex, we count up by 9. And you're going to get this parabola shape. So we're going to get some practice with this as we look at some of the other examples, but that 149 rule is definitely going to come up. The next one that we had graphed was the absolute value graph, and this is the one that was a straight line on both the left and the right with a slope of 1. And that's exactly what we're going to graph, is say when I do an absolute value, we want to think about this like a V, but not just any old V. It's a V that has a slope of 1 on the right and -1 on the left, meaning count up 1 over 1, up 1 over 1. Now when it comes to the square root, if you remember when we did our little t-table, we started off looking at some negative values until we realized, wait a minute, these are not real. And then we looked at very specific values for x, and hey, these should jump out at us. These are the same squares that we had for the 149 rule. But since we're taking the square root, we're undoing these, and that got us this shape that actually kind of looked like a sideways parabola, and that's not by accident, it actually is. This looks like a parabola that's on its side, but only the top half of it. And that's exactly what we would expect. And so our rule for graphing this is going to be based on the whole 149 idea again. But this time it's the x values, that our x values are 1, 4, and 9. And as we go over by them, we go one step up. So when we did 1 over, that was 1 step up. 4 over was 2 steps up. 9 over was 3 steps up. And so if you can remember that graph right there, that's what's going to happen every time we look at a square root. Now the way we're going to organize this part of the lesson is that for each of these examples, each of these transformations, I'm going to show you one example by point plotting, and again, point plotting is not how I want you to graph. The idea of the point plotting in this case is just to demonstrate how we can figure out what that whole +2 on this graph looks like. So that's the idea, is I'm going to do some point plotting now to kind of discover what's going on, and then we'll do an example where we show exactly how I'd actually expect you to do this problem. So I'm going to use a couple different colors so we can kind of see what's going on. In black, I'm going to go ahead and graph y equals x squared. So for practice, remember that this is the parabola with the 1, 4, 9 rule. So as I take one step over from the vertex, I go up by 1. As I take another step over from the vertex, I go up by 4. And another step over from the vertex, I go up by 9. And this is what y equals x squared looks like. But now on the same axes, I'm going to change colors here. I'm going to use blue. We're going to graph y equals x squared plus 2. And so again, for now, I'm going to do point plotting. That's not really what we want to do, though. So I'm going to pick my same happy values that I normally like to do. Now in this case, when I plug -3 in and do -3 squared plus 2, that's 9 plus 2, or 11. And if I keep doing the same thing for each of these, -2 squared is 4. When I add 2 to that, I get 6. This one's going to get me 3. This is going to get me 2, then 3, then 6, then 11. Let's go ahead and plot these. We have 0, 2, 1, 3, and -1, 3. We've got 2, 6, and -2, 6. And we've got 3, 11, and -3, 11. So when I play connect the dots here, this parabola looks like it has basically the same shape. The big difference here is that each of the ordered pairs that were on the original one, the black parabola, all those got lifted up by 2. It's like we picked the entire parabola up and lifted it up by 2. The other thing to note on the blue graph is that if we just focus on the vertex, 0, 2, the next set of ordered pairs are up by 1 from there. The next set of ordered pairs are up by 4 from there. And the next set of ordered pairs are up by 9 from there. So once we knew where the vertex was, we could still use the 1, 4, 9 rule from there to get the next ordered pairs. What this tells us then is if we have a plus after our function happens, so if you have x squared plus a number, that's how many units you've been shifted up by. And it's reasonable to believe then that if we have a minus after a function, that's how many units we shift down by. And that original function could be x squared, in which case we graph a parabola, or it could be an absolute value, in which case we graph a v that's just been shifted, in this case, down by 2 units. So this is called a vertical transformation or a vertical shift, when we're just shifting up or down. Now it is important to notice that that plus or minus is happening after the function. We're not saying, let's add 3 to the x and then square it. We're not saying, let's subtract 2 and then take the absolute value. We finished the x squared and then added the 3. We finished the absolute value of x and then subtracted the 2. So when the plus happens after the function, that's a vertical shift. So now in this example, I want to do this one the way I expect you to do this on your homework. What I want you to do is I want you to look at this one without point plotting and to identify what's going on in this graph. Oops. The first thing to identify is that this is a parabola. We're going to be using the 1, 4, 9 rule. The basic shape of this guy looks like that. That's the first thing I want you to identify. The next thing to identify is the -3 afterward. That means we've been shifted down by 3 units. So we're going to graph a parabola that's been shifted down by 3 units. The way that we're going to do that is our vertex is normally at the origin. So our vertex is now at 0, negative 3. From there, we're just going to use the 149 rule. We don't have to worry about the minus 3 anymore. We're going to say, if I take a step over, then I'm going to go up by 1 unit from the vertex. And that gets me my next ordered pairs. Now, if I take another step over, so that gets me in this line that I have the arrows in. That's my next step over. Now, from the vertex, I'm going to go up by 4. So 1, 2, 3, 4. And so that gets me my next set of ordered pairs. Now, if I take even another step over, at this step over, I need to go up by 9. So 1, 2, 3, 4, 5. Oops, I actually miscounted on that last one. Sorry. I make mistakes too. I only counted 3, and I'm supposed to count 4. That's why we have erasers. So back to where those arrows are. We're going to count 9 again. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And that gets me those ordered pairs. I can now connect the dots. And I'm going to go ahead and erase my little marks that I made for myself. And that's my final graph. We had the idea of a vertical transformation. We're going to shift our gears and we're going to go back to exploring something else. So in this exploration here, we're going to go back to the x squared graph. And we're going to look at what happens when we put a minus 1 before the squaring happens. So we're going to, again, I'm going to use black ink to graph my regular old y equals x squared. So this is our regular old 149 with the vertex being at the origin, at the ordered pair 0, 0. So this is our regular old parabola. And we want to explore what happens when we try to graph y equals x minus 1 squared. And so again, for the exploration here, we will go ahead and do a t-table. But again, like I was saying, this is not how I want you to do it. Hopefully I'm making that clear by saying it 6 billion times. Let's go ahead and start with our same old negative 3, negative 2, negative 1, 0, 1, 2, and 3. When I plug negative 3 in, negative 3 minus 1 is negative 4. When I square that, I get 16, which is well off my graph, but it kind of gets me an idea of what's going on. When I plug negative 2 in, negative 2 minus 1 gets me negative 3. Squared is 9. Negative 1 minus 1 is negative 2. Squared is 4. 0 minus 1 is negative 1. Squared is 1. 1 minus 1 squared is 0. Squared is 0. 2 minus 1 squared is 1. 3 minus 1 squared is 4. Now for the symmetry of this, we might as well go ahead and look at an x value of 4. 4 minus 1 is 3. Squared is 9. So if we start plotting these ordered pairs, we should probably quickly see what's happening here. Is we do still have a parabola. It's just been shifted to the right a little bit. Now it's important to notice that it's been shifted to the right. This might be a little counterintuitive at first because of the fact that we have a minus there, and minus we often think about as going to the left. But that's also why I did want to go through the point plotting. It becomes more obvious with the point plotting that that minus 1 counteracted the positive 1 that was there. When we looked at the ordered pair 1, 0, we plugged 1 in for x. The minus 1 brought us back to 0. And then we squared it. So we had to plug in a positive 1 to counteract the minus 1. And that's why this becomes a shift to the right. So to kind of summarize that, if we have a minus directly next to the x before the function happens, that's a shift to the right. If we have a plus directly next to the x before the function happens, that's a shift to the left. Now, one thing that I could kind of do to remind myself is if the plus or minus is right next to the x, that's a shift in the x direction. Whereas when the plus is afterwards, that's a shift in the y direction. But if your plus or minus is right next to the x, that's a shift in the x direction. Let's look at example 2 here. Again, we don't want to use point plotting. We want to go ahead and graph this guy as is. The fact that there's a square going on tells me that we have another parabola, so we know the basic shape of this guy is using the 149 rule. But now we have two different things going on. We've got a minus 2 directly next to the x, and we've got a minus 1 after the whole thing. That minus 2 that's directly next to the x, remember that minus is next to the x is the left and right direction. A minus means we're going to go to the right by 2. Whereas the minus 1 on the end says we're going to go down by 1. So to graph this without point plotting, we're going to go right 2, down 1, and that's where our vertex is going to be. From there, we're going to do the whole 149 thing again. So from there, if I take a step over in either direction, I go up by 1. If I want to take another step over, I'm going to be going up by 4. So 1, 2, 3, 4. And if I want to take yet another step over, I'm going to be going up by 9, so it's the 1, 4, 9 rule. So 5, 6, 7, 8, 9 gets me there. Gets me there. And now I can play connect the dots. And this parabola right here is the properly shifted, we shifted to the right by 2 and down by 1 parabola. All right, let's go ahead and look at the last type of transformation that we're going to discuss. Now for this one, we're going to start off with y equals absolute value of x, just for a little change of pace. We had a lot of the parabolas. So in black ink, we're going to go ahead and do our v that goes up 1 over 1, up 1 over 1 in both directions. And so we connect the dots there. We've got our nice little v going on. No curve to it, remember straight lines. And this time, the new graph that we want to explore is what happens when there's a negative out in front, when I'm multiplying by negative 1. So in this case, if I go ahead and look at my x and y values, I'll again pick the same x's, and we'll see what happens. When I plug negative 3 in, the absolute value makes it positive no matter what. But then the negative makes it negative no matter what. So this becomes negative 3. And that's what's going to happen for each of these is they become negative no matter what. So we take the same value and make it negative. If we plot those ordered pairs, we can see that we have an upside down v. So what that negative seemed to do there is that negative, that multiplying by negative 1, reflected us across the x-axis, which should make sense when we think big picture here. When we think big picture, when we're graphing the y values. If we multiply that y value that we are getting by negative 1, we're saying flip it, change the sign, change it from positive to negative. So we're flipping across the x-axis and getting a reflection. And so if we want to look at just the basic shapes we get, that if we reflect a parabola, then instead of a parabola opening up, we're going to get a parabola opening down. When we talk about a square root, instead of the top half of a sideways parabola, we'd reflect and get the bottom half. So this dotted line would be the x-axis. And what we just saw was, of course, the negative of the absolute value is a v that opens down. So a negative is just going to mean flip it, make it look opposite. Let's take a look at example 3. Now, when you're trying to sketch this graph without point plotting, we want to identify a few things. The first thing I want to identify is the basic shape. This is a square, but it's got a negative out in front. And so the basic shape of this thing is an upside down parabola. We're going to use the 1, 4, 9 rule, but really it's going to be going down 1, down 4, down 9. The next thing we want to identify is the +2 right next to the x. This means that we're shifting left by 2 units. And then the last thing we want to identify is the -1. This is meaning that we're shifting down 1 unit. So as far as graphing, let's start with our shifts. We went left 2 and down 1. There's our vertex, that's where we start from. And now we're going to do a parabola that opens down, so we're going to go down 1 over 1. If I go over 2, I need to go down by 4. And then I need to go down by 9. So 5, 6, 7, 8, 9 gets us here. And now we connect the dots. And that's the basic idea of transformations. The basic idea of transformations is going to be memorize your few basic functions and then just identify how has it been altered. Has it been shifted left or right? Has it been shifted up or down? Has it been reflected? All right, it's time to change gears now. We're now going to talk about variation problems. These variation problems are going to be talking about how different quantities vary with respect to one another. Now, this is all about proportionality, and you've solved proportions in earlier math classes, but very simple proportions. So you probably solve proportions along the lines of a 12-ounce bottle of ketchup costs $2. How much does a 16-ounce bottle of ketchup cost? Something along those lines. You set up a proportion by setting up a fraction equals a fraction, where one of the values in the fraction was a variable, and then you cross multiply and solve for that variable. That's great. There's nothing wrong with that. But the problem is that not everything is proportional in such a simple way. Sometimes, instead of something like with ketchup and price there, the amount of ketchup and the price, instead of it being as the ounces go up by a little bit, the price goes up by a little bit, maybe as the ounces go up, the price goes up by some factor of a square in there or something. Or maybe there's situations that as one quantity gets bigger, the other gets smaller, actually. Or maybe even there's 3 quantities involved or 4 quantities involved, and we've got to figure out how they're all related to each other. And so that's what we're going to be studying here in the rest of this lesson, is variation problems that involve those kinds of trickiness. And we're going to solve them by basically translating the words that are on paper into an equation. And so we're going to use some translation keywords, and we're going to say, all right, so here's these keywords of what to translate. It's basically our dictionary, our key here. And we're going to translate from English into math. And then we're going to solve those equations to solve whatever problems that we want to solve. So in these problems, there's going to be this thing called a constant of proportionality, sometimes called a constant of variation. And this is a constant, meaning a number, that stays the same for a given situation. So in our example of the ketchup, for instance, the constant of proportionality, or the constant of variation, is going to be how much per ounce does our ketchup cost? That's a constant that's going to stay the same. We're going to use the letter K to represent that constant. Now, the keywords that I have listed here are for every type of proportionality that we're going to deal with. When we see the word varies, the word varies is always going to be translated as equals K. This is where the equals sign in our equation is going to come from. And that constant proportionality is always going to come right after that. And if this is going to make more sense when we look at an example, but I just want to get this table together first so you have all of your keywords that you're looking for. You know what to look for. Now, sometimes, though, instead of the word varies, you're going to see the word is followed later in the sentence with the word proportional. So it might say is directly proportional or is inversely proportional or something like that. Wherever the word is appears, that's where you're going to write equals K. And then the other 3 keywords are the different types of variation that we're going to deal with. When you see the word directly, Directly means you're going to multiply by the next thing that comes up in the sentence. And we'll explain more of this in a minute. Inversely is going to mean that you're going to divide by the next thing that comes up. And jointly actually means you're going to multiply by the next two things that come up. You're going to look for two quantities, and it's going to be times one times the other. And again, this will make a little more sense as we start to get into one of the problems. So the first type of variation I mentioned was direct variation or direct proportionality, and this is kind of what we're used to thinking about when it comes to proportions. Now, an example of direct proportionality is y equals kx. So as your x gets bigger, so does your y, because you're just multiplying by k and that's all you're doing. If your k got smaller, your y would get, or sorry, if your x got smaller, your y would get smaller too. So this is direct variation. As one quantity gets bigger, so does the other. The example I have written down here is if x is the number of hours you work in a given week, and y is your amount that you get paid for the week before tax, then this could be a direct variation problem. Because as you work more hours, you're going to get paid more. And in this case, your constant proportionality is going to be your hourly rate. So it's not necessarily going to be 1. It might be 10 or 12 or 15. So that every time the x gets 1 bigger, the y, your paycheck, gets $10 bigger. So as you work 1 more hour, you get $10 more, or whatever your annual rate or your hourly rate happens to be. So that's kind of an example of what direct proportionality is going to be. Now there's some steps that we're going to use for solving these proportionality problems. So you're definitely going to want to have these written down. That step 1 is you're just going to translate. You're going to write what I'm calling the general variation equation with the k in it, but this is going to come from just translating the words that are on paper. Then what's going to happen is you're going to be given values. You're going to be given, all right, your x value is this, your y value is this for one situation. You're going to plug those in, and that's going to allow you to solve for k because k is the only variable left. Once you solve for k, you can put k back into that step 1 equation, that equation we came up with in step 1, and now you have a specific equation built just for your situation. And again, we'll see an example of this. I just want to get these steps written down so you kind of know what to expect. Now, I do want to point out, as far as your final answer doesn't stop at step 3. Your final answer is not ever going to be k equals. That's not a final answer. We're going to be asked one of two types of questions with variation. Either find the variation equation, or we're going to solve some word problems. If we're solving a word problem, then we're not going to answer k equals. We're going to answer with like blank feet or blank inches or whatever it might be. If you're asked for an equation, then we need to have an equation with the variables from the problem in it. We're going to start with a fairly simple, straightforward problem here. This problem says to find the variation equation, and we're told suppose y varies directly as x. So we're going to take that sentence, suppose y varies directly as x, and our step 1 is to translate. It's to write a general variation equation. So suppose is kind of a filler word. It's not important. So the first thing I see is the variable y. So I'm going to jot that down for my translation. The next thing I come across is this word varies. And if you look back to our table of keywords, varies meant equals k. And so that's what I'm going to write down. The next thing I come to is the word directly. And that said, multiply by the next thing that comes up. And the next thing that comes up is the variable x. That's step 1. Step 1 was to write the variation equation with the k in it. Step 2. Plug in the known values for our variable. We're told that the y value is 5 when the x value is 30. There's step 2. Step 3, solve this. So we're going to divide both sides by 30. And that gets me k equals 1/6. Again, this is not the final answer. Step 4. Step 4 is to take this value of k and plug it back into my original equation. So we're going to replace the k with 1/6. This is the final answer. This is the variation equation. This equation tells us how x and y are related. it says whatever your x value is, multiply by 1/6. That gets you the y value. Now we're going to talk about inverse variation. Now inverse variation is kind of interesting because now we're getting into something that's kind of new. It's kind of different from what we've dealt with back in pre-algebra. So an example of inverse variation is y equals k over x, because inverse, remember, in our translation means divide by, so we're going to divide by the x. Now the interesting thing here is that as our x value is getting larger, the y value gets smaller. And you can picture this when it comes to fractions by the denominator being the number of pieces in your pie or the number of pieces in your pizza. As you get more and more pieces in your pizza, the pieces are getting smaller. So the full value, the y value, is smaller the more you cut it into. So an example that we can look at here is speed and time. That if we have a fixed distance, like your distance to get home from work, then if you increase your speed, the amount of time it takes you to get home is smaller, provided you don't get a ticket. But if you decrease your speed, it's going to take you longer to get home. So this is an example that as one variable gets smaller, the other gets bigger, or vice versa. As one gets bigger, the other gets smaller. So let's look at an actual example on how we can use this for solving a problem. So our directions are, again, find the variation equation. And this one tells us suppose y varies inversely as the square of x. And so once again, the whole suppose part is just kind of filler words. We don't care about that. But then we see y, so we write that down. Then we get to this word varies, which means equals k. Then we come to inversely, which means divide by whatever comes next. And what comes next is the square of x. So we have x squared that we're going to put in the bottom there. There's step one. We translated what was given to us into an equation. Step two is then to plug in these known values. So we have a known value of 5 in the y and -4 in the x. So we have -4 squared. So if we do a little solving here, -4 squared is 16. If I multiply both sides by 16, I find k is 80. Now we just plug this back in and say, let's replace the k with an 80. And that's our final answer. Our variation equation in this case is y equals 80 over x squared. And so again, the basic steps here is step one is to translate the equation and just get an equation with nothing but variables in it. That's step one. Step two, plug in your known values. Step three, solve for k. Step four, plug that k back into the original equation. All right, so the last couple examples that we did were all about solving for equations. We were trying to translate an equation, we got a variation equation, and that's what we were going with. What we want to do now is talk about some application problems, some word problems. And this is our first really big foray into word problems in this class. So I do want to take a minute to talk about some general strategies when approaching word problems. Because I do hear from a lot of people, yeah, word problems suck, I'm not very good at word problems. So we're going to hopefully get better at word problems. We have 4 steps for a word problem. They're written right in your notes. Understand, translate, solve, and interpret. If you handle each of these separately, you can improve your skills within them. But you got to listen to my advice. If you think that word problems are tough and you have a hard time with them and you want help, then please follow my advice. Step 1, understand. We're going to read through the problem and understand what type of problem is it. Now, of course, like in this section, that's going to be pretty easy because it's going to be a variation problem. That's what we're dealing with. But in general, try to figure out and say, all right, I see the word varies, I see the word proportional, this is a variation problem. But the biggest thing
that you can do that I see a lot of people mess up on, especially in this section, is they don't define their variables. To define your variables isn't just to write an x and a y, or whatever the variables you happen to choose. It's to write it out in words. To write out in words, my x is representing blah. D is the distance from A to B. Not just distance. D is the distance from A to B. For V, you don't just say velocity. You're going to say is the velocity of the car. T, the time it takes to travel from A to B. You're going to fully write this out in words. And this is helpful because as you solve your problem and work on it, and you get some answer, you get T equals 7, you want to look back and say, did I actually answer the question? What was T even representing? So it's important in that understand step for you to define your variables. Now the translate step is where you translate the words into a math problem. And this is going to make it look just like any other normal homework problem. So you can solve it, get an answer. But then the other thing that makes word problems tricky is the interpret step. But again, this is where the understand step helps you out. In the end, after you get an answer to your solve, you got x equals 7, whatever you might get. You got to say, does this answer the question and does it make sense? In order to answer does it answer the question, you need to know what your variable is representing. Going back to your understand step, if you wrote it out in words, you know. You know, hey, my x represents this. Oh, that's not what I'm being asked for? Let me figure out what I am being asked for. Or, hey, that does answer the question. Great. And then you're always going to say, does this make sense? So if we're trying to figure out, for instance, how much paint do we need to paint a bedroom, you're not going to get an answer like 5,000 gallons. You're not going to go to Home Depot and take 5,000 gallons of paint to say, I got a bedroom to paint. You want to make sure your answer makes sense and it's reasonable. And so that's another important part of your interpret step.
So let's take a look at this word problem here. Now, we're going to start off in the understand step reading through it. The weight of an object on or above the surface of the Earth varies inversely as the square of the distance between the object and the Earth's center. If a person weighs 160 pounds on Earth's surface, find the individual's weight if he moves 200 miles above the Earth. Find the answer to the nearest pound and assume the Earth's radius is 4,000 miles. Okay, so we read through this and we see the word varies in there, and so we figure, all right, there's definitely some sort of variation going on. Now, you might cheat a little bit in your defining of the variables. You might do something like this and say, hey, all of this here, that's W, the weight of an object on or above the surface of the Earth. If we look through here, the other variable involved is the distance between the object and the Earth's center. It's important to see how this is defined. So it might be worthwhile to write it up here. We're going to call it D, and distance from center of Earth to our object, whatever that might be. All right. So there's what's going on in this problem. Now, there's an inverse variation, meaning as one gets bigger, the other gets smaller. Now, we should notice there's a square of that going on as well. We'll get to that in a minute. But now we want to get a ballpark idea. So part of my understand stuff is I always want to try to get a ballpark idea of what am I expecting my answer to be. So in this case, if we have somebody that's on the Earth's surface and they weigh 160 pounds, they move further away from the Earth, their weight should go down. We're expecting an answer of 150, 140, 130, something like that. That's what's going to make sense to us in the end. So, back to our problem at hand here. The weight of an object on or above the surface of the Earth is the first thing we come across. So as far as our translation is concerned, that's a W. Then we get the word varies, and we get an equals. It's always equals K. Then we get the word inversely, that means divide by the next thing that comes up. And the next thing that comes up is the square of the distance between the object and the Earth's center. Now the next part's a little bit tricky. We're supposed to plug in a known piece of information. Typically, it's going to be the next sentence you come across. And sure enough, it is in this case. We're told that the person's weight is 160. So there's their weight. Now the distance is a little bit tricky. It might help to draw a picture of what's going on. Here's the Earth. We're told that the radius of the Earth is 4,000 miles. So if we have a person standing on the surface of the Earth, they're 4,000 miles from the center. Oops, let me switch back to writing just to keep this consistent. And don't forget that that value was squared. So now we need to solve for k. We're going to multiply the 4,000 squared to the other side. Oops, too many zeros. Making errors all over the place. Now we could go ahead and put this value in the calculator. I'm not gonna, because it's just going to be some crazy big number. So I don't really want to do that. Instead, I want to take it as is right now and just rewrite it. And say W equals 160 times 4,000 squared over D squared. So this is the end of step 4 of our normal problems. Now for a word problem, we have one extra step involved. And that extra step is to answer the actual question. Find the individual's weight if they move 200 miles above the Earth. And this can be a little bit tricky because it's tempting to say our distance is 200. But that's not the case. Our person that was standing on the surface, this is not drawn to scale, is now 200 miles further. So from the center of the Earth, they're actually 4,200 feet. So that's what we're going to plug in over here, is we're going to replace the D in this equation with 4,200. Now we'll use a calculator. So we're just going to go ahead and use the calculator. Now a nice trick is if you do have the 30xs multi-view calculators, we can just hit the fraction button and type it in exactly as it appears. 160 times 4,000 squared. And then we just arrow down to the bottom for 4,200 squared. We hit enter and we get this crazy number that we don't really care about. But right above enter are these two arrows. Hit that, and that'll convert this into a normal value of about 145 pounds. Now, one last thing to talk about as far as giving an answer. Notice that I did not circle W equals. I made up W, so it doesn't make sense to say W. That'd be kind of like me saying, hey, how old are you? And you just say X equals 20. That's kind of weird. You'd say, hey, I'm 20 years old. And so the same thing here. If I'm asking you how many pounds this person weighs, say 145 pounds. Now there is a fourth type of variation that doesn't have a keyword associated with it that I just want to talk about real quick. And it's called combined variation. Combined variation is just when we combine direct, inverse, and or jointly in some way, shape, or form. And so what I do want to point out is if you see this word combined as far as combined variation, or if you see and in there, this never means two equations. You always only have one equation for any variation situation, and we're literally just going to translate. And this isn't confusing if you just translate what you see there, but if you try to memorize direct means this type of equation or inversely means this, then it can be confusing, but don't let it be confusing. Just translate. Just translate whatever is on paper and words into a single equation. That's all you got to know. Let's look at an example of combined variation. This is an example where we're going to have a few different types of variation within the same problem. And we're going to see that it just translates to a single equation. As you read through this problem, It tells you the maximum weight that a rectangular beam can support varies jointly as its width and the square of its height and inversely as its length. And then we're given some dimensions of one beam and asked to find out how much weight a similar beam can support. And while the numbers are going to get a little bit funky for a minute here, if we take a step back, we can see that this is actually a really good real-life problem here, where we could, in a lab, figure out by applying pressure to some sort of beam how much weight it can support until it breaks. And if we make the beam out of the same type of material, we can say, well, what happens if we make it a little bit longer than before, or a little bit wider than before, a little bit taller than before? How will that affect things? And now we can do it mathematically rather than wasting more beams. So that's the beauty of what's going on here. So we need to make sure to define our variables. Now, I'm going to define the maximum weight as a capital M. All the rest of the variables are going to be obvious because they're going to be width, height, and length, and so those are going to be W, H, and L. So the maximum weight is the first variable we come across, and it says that a rectangular beam can support varies. So here's that equals K that we like. Then we get this keyword jointly. Jointly, remember, means multiply by the next two things that come up. So first thing that comes up is the width, and the next thing that comes up is the square of the height. Now this word and doesn't mean anything to us. We come across the word inversely, and inversely is going to mean divide by. So we're going to divide by whatever comes up next. And what comes up next is the length. So there's our first step. We've translated what was in words into an equation. What we expect to have happen next is we expect one full set of information. And there it is. So we're told that we have a beam that's 1/3 foot wide. So that's the width. I'm going to put a 1/3 in here. We have 1 foot high. Our length is 10 feet. And the maximum weight it can support is 3 tons. Now this looks weird with a fraction within a fraction, but what I'm going to tell you is you don't need to solve this all in one fell swoop. Take it apart one piece at a time. Let's go ahead and just clear the fractions. Let's multiply both sides by 10. That gets us 30 on the left and 1/3 there on the right. And of course the 1 squared is just 1. Then we can clear fractions again. Multiply both sides by 3. We get 90 equals K because the 3's divide out. And now we have our value for K. Now we can plug that back in and rewrite our equation. Oops, let me go ahead and switch over to black ink so we have a differentiation here. We have capital M equals 90 times W times H squared all over L. Our last part that we want to do then is to plug in the partial information and solve for the remaining variable. So if we look at what's given to us here that I've underlined in red, we're given that on the new board, the width is 1, the height is 1/3, and the length is 9. Now this is again looking confusing, but if we notice that what's happened on the right-hand side there, on the right-hand side, I have nothing but numbers. I just need to calculate that value. And I have this wonderful tool for calculating values. It's called a calculator. Let's use it. Now we have a fraction here, so we're going to hit the fraction button. And we have 90. Now we don't need to put times 1 because, as we know, times 1 doesn't really change anything. So I have another fraction. I have 1/3. So I'm going to hit the fraction button and type in 1/3. End my parenthesis. hit the square. I'm going to arrow down to the bottom and press 9 and hit enter. And I get this answer 10/9. When it comes to a word problem, I don't want 10/9 as an answer. So again, I'm going to hit this button above enter and 1.1 repeating. So my final answer is 1.1 tons is what I can support with this new beam. And that answers the question.